It's my pleasure to be the first talk for today. Hopefully you all had your coffee. Otherwise, I hope to get your blood pumping. I won't mention that originally one of these physicists there. I can pass as a computer scientist most of the time by now, so I'll stick with that. And then I'll go back and do something for the company, as Robert put it. But for now, I'd like to talk to you about what we do at NVIDIA. We built CUDA-Q for one, like CUDA, but for quantum. It's a complete platform, programming model, compiler, runtime. They can connect to a range of high-performance simulators, of course, that we build, but also actual quantum backends. If you've been at one of our previous talks at some point, you probably have seen a slide similar to this. There are a lot of HPC centers that we work with. There's a lot of interest by now of having quantum hardware be accessible in the same kind of locations that other accelerators and high-performance computing tools are available. But what I'd really like to talk about today is a little bit more on the technical details and where we need to go as a quantum computing community. And for that, I'd like to start with a very high-level abstraction, essentially. Most of use of quantum hardware today looks something like this. None of us generally have a quantum computer in their basement. They need to be cool, they need to be maintained, they're kind of hard to build, I hear. So we usually access them remotely via some sort of service front end that then gets some input that it translates to an actual job for quantum hardware. There's probably a runtime there, some just-in-time compilation to actually generate the instructions to run on the quantum hardware, and that gets then handed off to what we can call the backend. And that's the part I first want to drill down a little bit on it, because we at NVIDIA have a lot of experience with accelerators. And that's the part that we find particularly interesting. We don't build quantum hardware at this time to preempt the question, but we like to work with everybody that does to figure out how to make full use of it, most efficient use, and there's usually a lot of classical infrastructure around it to do that. So let's focus on this accelerator process here. You see I made the distinction between real-time computation, and I already, a little bit forward-looking, put together an error correction outline around the actual quantum computation. Even if we don't have that, that doesn't really change much in the picture. But the important part is that what I call here quantum computation is the thing that actually happens on the quantum hardware. Some pulses, some fields, the actual quantum hardware usually doesn't store bits or anything like that. It's literally just a physical device for the quantum computing. The real-time compute, on the other hand, is what I call anything that has classical bits there and can talk to the quantum hardware. So your control system in some sense, but ideally at some point we also want that to be able to evaluate certain classical computations while the quantum hardware, retains its state. That would be very lovely. And then there's the host process, which is kind of the runtime here, I called it. And that's responsible basically for creating jobs for this accelerator piece, so to speak. And the important distinction here between the host process and this real-time compute is basically in process versus out of process, right? We can think about it from that perspective. Host process and backend generally don't talk back and forth while both retain their states. So especially in the early state and still with some hardware that is out there, when you send off a job, it's everybody who's ever asked for a circuit, that means that you ran your host code, you got a circuit, sent off the circuit, got back results, quantum memory is gone. It was a circuit, it was done afterwards. There wasn't any state maintained or anything like that. It's a one-time communication between the host and the backend that executes it. Now what I'm looking for here is a back and forth communication, basically, with the real-time system, right? Where you push down instruction back and grabs it, executes it, pushes back some responses, and the real-time compute pulls from that, takes action on that, sends further instructions, all while both maintain their state. And that's very, very powerful to be able to do that, right? Now, in part, why is this so important? Let me just give maybe a couple of motivating things here that you may have seen in publications about quantum applications or demonstrations on hardware and so on. So you may have read papers that did post-selection on one hand. Post-selection generally is very much expensive, at the very least, and also for the most part something that usually could be eliminated if you could just act on a measurement result, right? If you can look at your bit that indicates success or failure, for example, and say like, oh, that didn't work, okay, stop there, we're gonna try again, you know? Saves you the trouble of continuing execution for something you already know failed, you know? Or similarly, you know, try again. We know how to fix it, basically. We know this one didn't work, so, you know, do a minimal patch up, continue execution. Then, you know, sometimes lookup tables have been a way to work around the fact that there's, at the early stages, there was zero classical compute available while you ran your classical application. So if you looked at something like a phase estimation that required some sort of angles to be fed in to execute, and usually all of these were computed ahead of time. Before anything got sent to the quantum processor, you need to evaluate every single classical value. Store it somewhere, make it easy for lookup, and so on. And that's got two problems. So one, when you actually do have a program with arbitrary control flow, I mean, clearly you would need to evaluate each execution path. If it's a program with potential infinite loops, it's not clear you can, for one, and for another, well, you know, it's very expensive to just run all possibilities that the classical could, of branches that you could take during execution. So we want to avoid that. But also lookup tables are generally not very scalable, you know, so we want to get away from that. For that, we do need to do some very basic logic, at least, like addition, multiplication, all of these things. Then, last but not least, maybe surprisingly, when we first started running real experiments with the state-of-the-art hardware, code size was actually the thing that pretty quickly became a problem, potentially. Not amount of qubits, we know that. We know how many qubits we've got to work with. We can pick applications, fit, you know, classical registers. That was also interesting that there's a limit amount generally available, but that's fine. But the code size, if you need to unroll every single loop, inline everything, flatten out everything, your code blows up really, really fast, you know. And that's a nightmare to develop, on one hand, reading through these, 10,000 lines of instructions and figuring out where your bug is. But it's also a problem just to actually have that code be readily accessible for efficient execution, right? And you see, I put that here as some motivations for needing real-time compute, and error correction isn't even on that. I'm going to get to that because a lot of the prominent questions right now is, well, where does error correction fit into this picture? Well, I'll come back to that. But first, I want to take away to be, look, applications in the end are not only quantum. Quantum is a subroutine. We read classical. None of you sees a quantum state. So somewhere there's a translation, at the very least, of output, so we actually understand it. We do want to be able to have a live communication between some classical logic and quantum processor. So the quantum processor can focus on doing what it's good at, and it's usually not arithmetic, you know? So being able to get that does open up a whole new range of applications that I think is somewhat under-researched at this time because these needs haven't been available. Well, good news is now there is hardware that can do that. There are starting to be some really, really fancy real-time systems out there that I'm very excited about. So I really hope to inspire some people here in the room to actually start thinking about adaptive algorithms, things where you act on measurements, on partial measurements in your system, and start to develop heuristics, because there's a huge potential in heuristics. Quantum computing started out in theory lab. It started out in provably better scaling algorithms. But if you look at all the classical software that's out there, all the optimizations, compiler work, and so on, hardly any of those are provably better. A lot of it is just smart combinations of things, basically, put together, that end up performing a lot better than if you just did one gigantic, very fancy math problem, basically. And now that we start to have the hardware, that's what needs to be looked at, right? I think there's a lot that we can do with today's quantum hardware. All right, so I promised to talk also a little bit about the more eminent things, like, well, error correction. Yes, when we do error corrections, just to be very clear, the corrections need to be applied in real time, in case that's still any question. I was very surprised a year back where I actually had a surprising conversation where it turned out it wasn't clear that you can't just all do it post-processing. No, you can't. There are certain instructions that you need to apply to the quantum hardware that you won't be able to apply correctly unless you have an actual correct state at that point. You don't necessarily always need to apply the correction to proceed with your application code, but you do need to have the option to have something that talks to the decoder, send down instructions to actually patch up the state. Then, yes, fancy before error correction, there's of course kind of optimal control, just making most out of hardware. I won't go into too much detail on this one. And I would like to instead focus a little bit on the abstract of, okay, this is all good and nice, but how do we get there? How do we actually hopefully not indicative of how to get there, okay? Blank screen. All right, first step, envision the future. Hopefully there's some vision spawning up in your head, or probably already had one. This is all nice. Let's keep in mind that what we build today will be the state of the art for future quantum computers, especially when we talk about building compilers and software stack and so on. It generally takes more than a couple of weeks to build this, right? So if I need to have something ready in 2 years, I better start building it today. But that also means that when I plan what we're going to do next, it's very important, of course, to support people with what they do today, but if I start building today what people need today, it's not going to be ready anyway. So basically, I'll try to extrapolate and speculate of, okay, what do people need in 2 years, and start building that. There's also practicality, however, right? So there's this nice picture, especially among software people. I think you've probably seen something like that. How do you build a car? It's probably not great to start with a wheel and add some, infrastructure around it until at the end of the day, the last step, you finally have a car. Instead, you probably want to start with something that rolls. That's a good start, maybe manually powered. And then you take it from there. At some point, you make it easier to accelerate that, add a motor, and this is going to morph and evolve over time, right? The same is true for quantum computing. So basically, if any of you is in the room right now and has to, well, this is all good and fine, but first we need the hardware, and then once we got the hardware, we can start, we can build the software. It's not that hard, right? It's software. How hard can it be to build it for the quantum computer? That basically is a little bit the mindset of, at some point on day X, there's this car dropping off down from the sky, and that's generally just not what happens. You do need to try and connect pieces early on. The very least also to help us be a little bit faster with developing quantum computing, right? When I did my PhD, it was still very, very usual to spend 4 years of your PhD hand optimizing an application, a single one, to figure out if it was good. Me being lazy, I was like, no, I'm not doing that. I'm not spending 4 years, having instructions there. I'm going to spend 4 years writing a compiler and then run it once at the end and see if it works. And that's how I got into compilers. So then, important step on practicality, I think. Growth in stages. So when we have the requirements, I talked a little bit about, what do people need today, what do people need tomorrow. And I think one thing that will be helpful here is for those that are familiar with fitting and overfitting, to maybe keep that picture a little bit in mind. Because there are kind of different points in time where we have different needs. If you hit everyone perfectly, it's going to be very hard to actually have a good progression of the things that we build, At the same time, it's also not an option to just say like, well, I don't really care about it today, just, there's where I want to go and let's just go build it, right? There's a happy middle ground of trying to meet most of what we need, make that work well enough, but also keep a trajectory for where we need to be in the future. So I think picture of fit it well enough, but don't overfit it is actually helpful. Then last but not least, I know I'm preaching a little bit here, but I don't think there's a single entity that will ever build for quantum computer all the applications, all the HPC integration, and whatever we need for it, all in one place. Even if it's one place, this is still hundreds of people at the very least, probably thousands. Also, you all are very talented PhD students here, so hopefully some of you will actually have major contributions to making this happen. And I don't know where everybody is right now. So to make this work, the important part is basically we win if quantum computing becomes successful. I really don't care who builds it. I just care that quantum computing works, in a sense. What's also helpful is that all the different people with different skill sets can actually contribute to something that complements other people's efforts and fits together. So here's where the bad word, I titled it unifying ecosystem because it's still a very bad thing to say. We need some standardization maybe will come in. This is not an enemy. Standardization is not somebody dictating. I know it's got that reputation, but that's not what it's about. It's about having a mutual understanding of where it makes sense to break down a problem. Compilation optimization is a really complicated qubit problem. Once you get past 50 qubits, you're not going to brute force it. You're not going to find the best solution for your optimization problem almost by definition. So the key to doing a good job with building software is to know where to break the problem apart to make it solvable, where to approximate. And this is where I think the conversations on kind of these standard interfaces is very, very important because it's really a conversation about what simplifying assumptions do we make to solve this problem? What's the right connecting pieces here, right? So, interesting area. All right, I'll keep this very short. All of these things is a little bit what we try to do with the QR Alliance. One very important thing we wanted to accomplish is basically we felt quantum computing was becoming big enough, complex enough, mature enough, if we want to call it that, to merit going to leverage existing technology. At the beginning, when there's very limited things quantum hardware can do, it makes perfect sense to just build the software from scratch exactly to what we need. But in the end, hopefully, the complexity of quantum applications will be comparable to the complexity of classical applications and a lot of rigor. And so we didn't really want to stay on that trajectory because I don't think it's very reasonable to try and rebuild decades of compiler research. It's just going to be decades behind. So there's a lot of tools that we wanted to leverage with the ecosystem. At the same time, it was really important to us to not limit kind of what we look at, right? So different instruction sets could be very important for different hardware. Different backends we still lack the formalization for what a quantum processor architecture actually is. So if you think of the target triple, we haven't defined an LLVM target triple for quantum processors. At some point we need to do that, right? Get conversation. So it's not the goal to say like, we know what we need today, it's all nailed down, here's exactly what it needs to be. It's a commitment to work together to figure out, how do we get from where we are today to much more complexity, leveraging all the tools at our disposal. All right. Promising to keep it short, I'll go to the CUDA-Q toolchain specifically. So how does this look like? One, we do have front ends, as I mentioned, currently in C++ and Python. Doesn't really matter what the front end language is. We do use the language-specific tools to get the first abstraction of what the application code is and translate that into our own MLR dialects, actually. So when I said before, there's QIR, yes, there is. We are using that, but it's just part of the stack. It's somewhere down here. So going a little bit through this, MLR gives us basically the platform-specific abstractions. It allows us to create abstractions for things that we're find particularly useful for optimization or for keeping a representation compact or knowing exactly what the source code was, right? These abstractions gradually get eliminated basically during compilation. We use the information that we have to optimize and then progressively lower as one does. Now, the code that we have being in C++ and Python encompasses not just the parts that go onto quantum processors, but also encompasses all of the host code, other accelerator code, like actual CUDA code, and so on. And with CUDA-Q, we have the same model as CUDA in that certain kernels are basically marked at the application level as being intended for execution on the real-time system of a quantum processor. And we do basically have a split compilation model that we get the full representation of all the code, walk that, extract the pieces that go to different processors, and send them to different compilers. So basically all the kind of host code gets just lowered to LLVM. Clang is doing that for us. We don't do any very special work here aside from a little bit of patch up to make it all connect. The GPU code, and there's NVIDIA IR. It's GPUs also, there's a defined subset within LLVM that generally GPUs can deal with. So here with QIR is basically the same model. The only purpose of QIR is to say what we use within LLVM, because LLVM is great but also huge. So the idea is not to use all of it. The idea is to use a subset, and then depending on the backend, actually this subset is either pretty limiting or a little bit more expressive, and that's what we compile the quantum kernels specifically to. We do also have option to emit other formats. Definitely reasonable to do that, especially as long as it's straight line code, so no control flow. We don't really care what we emit as a format, but as soon as we start to have meaningful control flow in there, this gives us a lot to work with. Now, where does it go from there? So on one hand, there is assembly for general CPU code. Usually this is not literally a stage in the process, but I'll put it there because it kind of gives the right picture on where it goes. There's PTX for GPUs, and then there's a big question mark for the quantum processors right now. So what's this question mark actually like? Well, the thing is, when people today talk about most IRs in quantum computing, we still have this very imperative representation, basically one instruction after another. If you have something like an H on all your qubits, you probably still have a for loop, for qubit in qubits, H on qubit, So most quantum programming frameworks, if not all, actually don't even expose vector instructions. And quantum computing is even much more interesting because generally we do have something like, multiple instruction, multiple data on all the backends. So usually I can do an H on qubit 1 and an X on qubit 2 at the same time, roughly speaking, within that model. But the IR representation for that is not generally something that's talked about a whole lot. We start to talk a little bit about timing information, but it's still sort of pieced together from there, right? So you might have an IR seeing the instruction, you can analyze dependencies to know what you can execute in parallel. Maybe you even have means to force some timing or synchronization, but that's it. That's still not an actual instruction buffer that goes to the hardware. At some point, something has to say, here's the clock cycle of my quantum backend. Here's what each and every bit, or qubit in this case, does during this clock cycle, and make it really efficient to apply that, right? So whether that be a pulse level representation, I hope in the end it's still a finite quantum instruction set that we will be dealing with effectively. But how to make that part efficient, I think that's something that we'll be allowed to talk a little bit more about within public venues. Everybody who's working with quantum hardware definitely has something for that. We're running somehow, after all. But it's not necessarily kind of shared that much. So regarding where does the error correction come in? Well, there's today and there's in the future. Ultimately, error correction, I think, needs to sit below a fully scheduled and basically a hardware-bound representation of your application code. The reason being, especially if you have qubits that need to be cooled or somewhere in a cryostat, there's only so many wires generally that you can get down. There's bandwidth. If we send down physical instruction, I think you've got a huge bandwidth problem, ultimately. Maybe not today, but in the future. So what needs to go down into the cold, I know not every qubit architecture is cold, but a lot of them are, that needs to be compressed information, so kind of logical level. And then somewhere, preferably harder, firmware, eventually, there's where the actual translation to the physical instructions would sit. Now, we're not going to start out that way, usually. Today, we do a lot of research on error correction. We need to be able to quickly iterate, try out things, and so on. So that's why today, error correction very much is treated just like another application. Write the application code for it, run it, see how well it does, and that's perfectly fine. But then we don't need to talk about error correction too much. Then it's just an application. The compiler doesn't care what the application do that you run. It just cares what it contains. In this case, it's an application that is adaptive, contains control flow, and maybe some minimal sort of bit manipulation to figure out what the next branch is that you're taking. All right, so just kind of the other picture. Why do we have MLIR in the mix here at the top? As I mentioned, LLVM is very, very stable at this point. So also, especially kind of 5 years ago when we started talking about QIR, felt like a good choice to standardize on something that is pretty stable at that point. And MLR kind of sits on top with the goal to allow customizations. There to make it really, really easy to have language-specific things expressed well and useful. So we want this flexibility to basically create whatever abstractions we want, but for the same reason, this is also where there's more deviation. Different front ends are going to have slightly different representations, what interfaces are kind of shared or should be the same. Maybe the interface for plugging in a layout compiler pass is something that should look roughly the same everywhere. So bits and pieces can potentially be standardized in that. Open conversation, if you're curious about that, come find me. I'm always happy to chat about opportunities there. But for now, we leverage it basically to meet the need of the front end so far. So please don't go and take a picture and say like, yeah, this is how NVIDIA said you need to do the compilation. Compilation is kind of a complicated thing and not that straightforward as just a list of things that you do. This is just to give an idea of there's a lot happening that we actually need to do. And I did want to give you an example of, why should you care about the compiler? Why is a compiler good? So one thing I'd like to talk about is kind of qubit management, because it's a very interesting problem that I hope some of you will find interesting enough to actually think really, really hard about, preferably the people also with a computer science background. Not that physicists shouldn't, but I think there's a lot that we can learn from computer science. Today, quantum programming software frameworks, most of them don't necessarily have managed quantum memory, as in, you've got this magical pool of qubits where you just say, get me 10 qubits, and then at some point it gets automatically cleaned up. Within CUDA-Q, we actually do have that at the language level. You do just that. You say, I need a vector, 10 qubits, and then at some point when it goes out of scope, the compiler automatically deallocates that. You as an application developer just need to be careful to actually make sure it's either measured or set back to 0, otherwise you've got it back in the application. But why is it interesting to think about managed quantum memory? Well, so for one, if you don't, it's not that you don't do memory management, it's just that the application developer needs to do the memory management. Instead of the compiler handling it, it's the person writing the code. If you need to specify, I'm taking qubit 5, a physical device, qubit 5 for this, qubit 6 for that, and so on, right? The problem with that is it basically makes it very practical to actually have libraries and share code. Because if you do need to make the decision of what exactly the qubit is that you use for each part of your application, you need to know what each part of your application does. You need to know when it runs, what runs concurrently, what other pieces happen at the same time, and so on, right? So what do you do if you just want to write a kind of a subroutine that takes temporary qubit, or needs a temporary qubit, does some computation with data qubits it gets as an input? Well, you could take the temporary qubit as input as well, right? But then again, somebody who calls this function needs to decide what's this temporary qubit that I'm using here. Which one is it? How does it fit together with everything? And I think that really prevents us from actually having shareable code, where somebody who's specialized in a particular subroutine just writes the most efficient implementation of that subroutine. It also prevents us from making pretty flexible choices regarding, do I take some additional qubits here to reduce runtime, or do I reduce numbers of qubits at the cost of a little bit of additional runtime? If we don't need to define this when we write the subroutine, the compiler in principle can make much better choices regarding how to get your space-time into a square. That's the bottom line. You want every qubit to be busy all the time. That's the whole goal. And while for any given problem you'll always be able to find the best possible solution by hand, question is in what amount of time on one hand, and how that having the option to have a good solution quickly and try out several application solutions basically will generally lead to faster progress in terms of identifying applications than if you need to go and really do it all manually. All right, I won't talk too much about the split compilation model. I mentioned that. We do a lot of just-in-time compilation before it goes to hardware to simplify the code that actually goes down to a real-time system as much as possible. But I do want to quickly summarize things in the front end that we get with that. So I mentioned, on one hand, we can integrate with all the standard tools, which is nice because there are a lot of HPC libraries and so on for these. It's also easy for us to kind of seamlessly transition between different tools, processors, and so on. We take care of that automatically by basically having our compiler or runtime handle the coordination. We check that during compilation for the most part. And that allows us ultimately to actually support advanced functionalities in the execution environment. So what I mean by that is if we do have a backend that actually has support for real-time compute or kind of mid-circuit measurements, as some of you put it, then yeah, we can absolutely send down code with these things in it. If not, then the code in some cases can be simplified to run at the cost of overhead, like lookup tables. And sometimes we'll just kind of effectively compile or say, look, this is not going to run well on this backend, you know, and reject the code during compilation. And I think this is very important because it allows us to work with the latest features that hardware has to offer, experiment with that, but also not require it for the integration, right? So, yeah, couple of little data points. So on one hand, we do have common patterns that are in applications such as computing expectation value, sampling, and so on, are of course performance optimized. Especially along with the CUDA-Q toolset, there's a whole range of high-performance simulators that come with it. We do all the trickery that we can to make it run faster on simulators, but the important part is we also do have the option to not do that and run the same code on actual hardware backends. So while we clearly look up states and cache states and so on for simulators where we can do that, our compiler is also perfectly able to handle needing re-execution if we have real hardware where you can't just grab the state. With that, we get some pretty decent performance numbers from the last couple of releases. These are actual numbers that we have, so we've done some great investments in that regard. We also use these common patterns, basically, especially for processing. So this too is an actual scale of the runtime. So for example, for computing observation values, multi-term operators, we do have all the performance optimizations to just send that as one query to the GPU and get back results this way, which actually makes a huge difference in processing time. So yeah, fancy GPU optimizations is generally what we do with all the tools. Right now, a lot of them are strictly on the simulators. In the future, we're working on GPU optimizations everywhere where it makes sense, and there's a lot of optimization problems that benefit from that. So over time, also some of these pieces will be relevant for quantum hardware. As I said, we do also easily kind of parallelize. We distribute across multiple nodes, multiple GPUs. You do have all the standard means to control that with MPI, actually setting up the distribution yourself. But to an extent, we also have some automatic handling of that, where you just get a certain number of GPUs, we'll spread the state, make sure it runs efficiently across all these resources. And then last but not least, we do have a range of simulators that are specialized and allows us to go to pretty decent sizes. Tensor networks being one of the popular methods to actually get some really good performance for certain kinds of problems. We started to expose some APIs to actually query a platform, basically, and say, I've got a platform, basically, 2 GPUs, a QPU of this architecture, and that this is still work in progress. So right now, the API is pretty basic. You can get a connectivity, you can query how many QPUs you have in there, but that's pretty much it. But over time, the intent is here to also provide the tool set that would allow to basically experiment with how to distribute on a bigger system. In particular, what you eventually should be able to do is to say, okay, let's say I've got 2 QPUs, and I'll model them with this simulator and this simulators. How would these play together well as part of an application, and experiment with that with some manual control there as well. All right. Summarizing, CUDA-Q, on one hand, we hope to have a somewhat seamless experience developing for multiprocessor systems consisting of CPUs, GPUs, and QPUs. and we can target QPU architectures with and without support for real-time computations. And we do have a lot of tools to start experimenting with today's hardware, but also with bigger systems and how they could be composed and efficiently used. And we do try to have automatic optimizations for some of the very common patterns and abstractions that are there. So naturally, you tie with all the HPC tools. If that sounds appealing to you and you want to start experimenting with that, we do currently ship Python wheels via PyPy. We have a Docker image. We even have actual continuous deployment where every time something gets merged to main, there's a nightly build for that that you can pull and start to experiment with. And then this whole thing is, for the most part, open source on GitHub. Some of the simulators are not necessarily. Some of the NVIDIA libraries for GPUs aren't, but the actual compiler, runtime, infrastructure, anything quantum specific, basically, that's all open source. So go check it out. And yeah, I hope to see you participate in the next Unitary Hack or other hackathon and actually pick up some of the issues that we have there.
Thank you.